All right, so here we go. Unit 8, electric charge and electric force. We are on part 4, which is Coulombs force law. So we're definitely on our way. Well, let's move on. Okay, so Coulombs force law. Okay, so in 1785, Charles Coulomb determined the relationship between distance and magnitude of charges and the force. So we figured out Coulomb's force law. The experiment apparatus Coulomb used is called a torsion balance. So we got this thin wire. The angle of the wire turns in proportion to the repulsion force. It's kind of like that thing we talked about in the other video. Light glass rod with identical metal spheres on its ends. Okay, so he did this experiment. He knew that they were charged, and the glass kind of made it so the charge didn't necessarily wander. Right there we go. Okay, now experiment. You can see he's got these different levels. He's got 10. Supposedly he did 10 different experiments. Charge was 1 unit, half, quarter, and you're like, well, how did he do those? Well, you understand that the Q, he didn't know what it was, so it was some value of Q that he referred to as 1, and charge Q2, distance, and then he measured the force, which is kind of like how much that thing was sort of torqued, and that's how he got it. And he did everything in nice little clean units. Yeah. And from that he got the equation that we're about to go on to. Coulomb's data. The magnitude of electric force that point-like object 1 with electric charge Q1 exerted on point-like object 2 with electric charge Q2 when they are separated by distance r gave the expression of this. And this is Coulomb's law. Now this is kind of weird. You don't usually see this Q1 on Q2, but it is still correct. Kc, we'll talk about that. It's not about chicken. Well, that was a really bad joke. Q1 and Q2 and r squared. Now it's important to understand that those are both absolute values. Kc is proportional constant called Coulomb's constant, whose value using SI units is that big honking number. So millions, 6 billions, 9 billion, I think, right? Okay, so that is our Coulomb's constant. When using the above to determine the magnitude of electric force, we do not include signs of the electric charges Q1 and Q2, which is why we have that absolute value sign. That's important to understand. We need to understand that 1 and 2, if they are both negative, they would repel. If they are both they're different, positive and negative, then they would attract. And that's important to understand because you have to sort of visually inspect that, as you say, to see that. Tip. If the interacting objects are large conductors and near each other, the electrons will redistribute on the surface, making the effective distance smaller than the distance between the center of the object. So that's important to understand. So just because it's different center, if they're metal, if they're conductors and they're large, that distance can all of a sudden change. So if you have a big sphere, you're looking for the distance between the charges. Whereas usually, that's why they use the word r for radius. Then it's usually referring to the distance between the centers. But that's important to understand. If it's a large object, you have to use a different distance, making the effective distance smaller than the distance between the centers of the object and difficult to estimate. Thus, we only use Coulomb's law for point-like objects. These objects can be either conductors or dielectrics. All right, here, comparing the magnitude of electric force to the gravitational force. So obviously the equations are very, very similar looking, and you're going to see problems that are also similar. Consider a proton and electron in a hydrogen atom. They are separated by about 10 to the negative 10 meters. The electric force between the two objects is 2.3 times 10 to the negative 8 newtons. And the gravitational force between these two objects is 1 times 10 to the negative 47th newton. So there is a difference, obviously, between them because of that constant and the charges. But it is important that those equations are similar, but the electric force and the gravitational force are very, very different. This one is, that's what we call teeny tiny, itty bitty. And that one is, okay, so that's still teeny tiny, but it doesn't get the itty bitty, right? And you're wondering, man, I wish I was in class to watch this video, to watch this, because I know Mr. Cooper wouldn't do this in class. Yes, I would. You know I would. Moving on. The electric force between these objects is about 2 times 10 to the 39th times greater than the gravitational force. So it is a gigantus times bigger, right? It is huge. They are similar equations, but they are still different because the forces they generate are often very, very, very different. And it shows you that with the hydrogen atoms separated. All right, since Coulomb's law contains the product of two charges, the electric force that object 1 exerts on object 2 is exactly the same in magnitude as the force that object 2 exerts on object 1. And that's the same with gravity. Coulomb's law is consistent with Newton's third law, which is also where kind of gravity comes from as well. So they do. If one pushes on the other pushes on the other, it's the same amount. All right, conceptual exercise. Two small aluminum foil balls of equal mass, A and B, have electric charges plus Q and plus 3Q, respectively. If balls are suspended by equal length strings from the same point, will one string have a greater angle from the vertical than the other? Justify your answers. Your answer. So this, oh good. Pause. Oh, by the way, yeah. So pause here. Try to do it on your own. If you're like, I'm totally lost, then try to stay with me for the picture and then try to do it on your own, because I know the picture can be a little confusing on some of these. So let's try to look at what this picture would look like. So we have our two balls, right? We have A, we have B. One is Q and one is 3Q. So these are both positive charges. So they're going to repel each other. You should know that. They're protected by strings. And here's your vertical axis, so to speak. And that's theta A and that's theta B. My distance is R, AB. Boom. And there's your picture. Try to do it from here on your own. Draw a free body diagram. Use the equation we just talked about. Try your best. If you get it wrong, that's good, actually. Then there's room for you to grow and get things right. So I'm going to draw my free body diagram. Obviously, this is A. So that is going to be my tension, my force tension of the string on A. Going down would be my force gravity on A. And that way would be my force B on A. So particle B on A. I have another one which is going to be very similar. A tension string on B, gravity on B, and there is my force of A on B. Now, force AB, A on B, would equal this, right? You've got my K, the Kc, the Coulombs constant, the charge on A, the charge on B, R squared AB, because that's what the equation was, equals. Wait, Mr. Cooper, that's like the same thing. No, that's not the same thing, right? That's B on A, right? So that's obviously the same thing. So, oh, yeah, Newton's third law. These two forces would be the same. Obviously. The electric force that one ball exerts on each other have the same magnitude according to Newton's third law and Coulomb's law. So they kind of coincide, which is always a good thing. Generally, when laws conflict, they're no longer laws. That's like bad. So since the balls have the same mass, Earth exerts the same force on each. So you have the force going down and the force going to the left or right is the same. The forces exerted by the strings must also have the same magnitude, since the net force exerted on each ball equals 0, because it's static. Therefore, the angles of the string relative to the vertical should be the same, because they're each pushing. The things that's making it swing is this, and the gravity doesn't act any differently, and these forces act the same. All right, let's move on. Conceptual exercise part 4. Now, this one is weird. Now, you have to slow down. Go with me. I did my best to draw this one out really nice and typed out. Probably took me longer than I should have, but it's okay. But you're going to have to do some rewinding on this one. You can't. It's hard to go through this one perfectly. 3 identical metal spheres, A, B, and C, are on separate insulated stands. You can charge sphere A with charge plus Q. Then you touch sphere B to sphere A and separate them by a distance D. Write an expression for the electric force that separates the force that the spheres exert on each other. Now, there's a second part to it. You now take sphere C, touch it to sphere A, and remove sphere C. Then you separate sphere A and B by a distance of D over 2. Write an expression for the magnitude of the force that separates A and B exert on each other. Now remember that charge must remain the same. So let's try to go through this here. There's my A, B, and C. So now I have A, which has plus Q. I touch it to B. And then I have Q over 2 and Q over 2, because charge has to remain the same. So it kind of equals itself out. I have a distance D. So let's just go back real quick, because I know this can get a little bit confusing. 3 identical spheres. You charge sphere A with charge Q. Then you touch sphere B to charge. You charge sphere A with charge Q. Then you touch sphere B to sphere A and separate them by distance D. So when you touch it, because it's conserved and it was equal, boom, A and B. Now what happens, you have that same thing, right? Only now C comes into the picture, you touch it. So again, your charge has to be maintained, your conservation of charge has to be maintained. So this is going to be halved, and that other half is going to go there. So now I have same B, because B wasn't involved. The distance is D over 2. Only now that's plus Q over 4. So now I have 2 different setups, and I have to figure out equations for them. So Q over 2 divided by, and the distance of D, Q over 4 and Q over 2 distance of d over 2. So it halves the distance. Okay, let's try to do this. So force A on B. So if we go back here, A and B, right? Force A on B will equal B on A. We know that from the last one, right? Newton's third law. So K equals Q over 2 over Q over 2 d squared. This is the first part, right? So that's why it's d squared and Q over 2, because they're both, if you remember from your picture here, Q over 2 and the distance is d. Boom. Now, I could do some, funky stuff, and Q squared and 2 is 4. Hopefully you kind of understand that. That's not too crazy algebra. And then that does not look very good, right? Your math teacher would be going, oh my gosh, that's like, I don't know, an improper fraction. I don't know what they always call that stuff. They're crazy. Don't tell my wife I said that because she teaches math, obviously. So this would be K squared over 4d squared. Boom. Easy peasy, melon squeezy. Now we're on to the second part, which is A on B, B on A. We know there's the constant K, only this time we've got Q over 4 and Q over 2 divided by d over 2 squared. Huh? Whoa. Just slow down. Look. Q over 4, Q over 2. The distance is d over 2. So we're plugging it right back into that Coulombs law equation. And we get some more funky stuff, right? Like this squared would obviously be d squared and 2 squared is 4. Boom, boom, boom. Now, we just, copy, change, flip if that makes you happy, or there's other ways to do it. But you work these out and you end up getting that. Boom. Not too hard, just some ugly algebra. Or maybe it's beautiful algebra, depending on your opinion. All right. This one is good. Metal spheres on insulated stands have the following electric charges. QA has +2 to the -9th coulombs. QB has +2 to the -9th coulombs. QC has -4 to the -9th coulomb. 10 to the negative, yeah. The spheres are placed at the corners of equilateral triangles whose sides have a length d equals 1m, with QC at the top of the triangle. What is the magnitude of the total net electrical force that sphere A and sphere B exert on each other? Now, this is what the picture looks like. Now, I'm hoping at this point in time, you may have seen a problem just like this, only it has planets. Because this is the way AP can be mean to you. They could give you the same problem and then say one's charges and one's gravity, but they're solved the same way. So this isn't too bad, right? We have these different charges. Now understand, this is positive, this is negative. This is positive, this is negative. So these are going to be attracted. So they're going to be pulling it down this way and pulling it down this way. And it wants to know the net charge that's on there. What is the magnitude of the total net? So after everything's all done, what's it going to look like? What is C going to be having on it? So we're going to take this down. Here we go. We have our picture. Oh, by the way, you should probably pause it here. Try to do it on your own. If you need help with the free body diagram, then pause it. But you want to try this on your own. All right, so we have our axes here. This right here is force A on C. So dealer, feeler. A is doing the dealing. C is doing the feeling. It's being pulled down. Because obviously this is C. That's 30 degrees. How do I know it's 30 degrees? It's an equilateral triangle, right? Okay, moving on. So that's 30 degrees right there. That's 60 degrees. Oh, I'm sorry. Tiny, but you have the, yeah, 60, okay, there you go. I'm sorry. I was just going crazy there. Okay, there's 30 degrees, there's 60 degrees. There's 30, force B on C, there's 30, there's 60. That makes your, 60 degrees, right? And that's a complementary angle type thing. Okay, good. So there's your focus on C. That's what's going on. Now, hopefully at this point in time, force A on C has got to equal B on C. Why do they have to be the same? Well, think about it for a second. Go back to your picture back here. Because both of them are the exact same charge, right? And they're the exact same distance, correct? So they're both going to be, the forces, those two arrows are going to be identical to each other. So they equal the same thing. So KC equals AC, those are the charges, together, D squared. Okay? Now, force net on CY. By the way, so QA could be QB, okay? But it's on C. So that was A, B, and that's C. So it could be QA or it could be QB. It doesn't matter. It's the same number. Now, force net on C. So Y, because ultimately, if you think about this, the force is going this way to the left and this way to the right because these things, right, are equal. These are both going to cancel out. So the only net force you're going to have is in the Y direction because basically A is pulling it to the left, B is pulling it to the right. They're going to be the same in that component, but Y, they're both pulling it down. So there's going to be a net force there. So if I want the Y component of this force, then it's going to be using sine of 60. So if I'm going to use, this right here, sine of 60, so some old horse, so that's my opposite, and I want this opposite side. Yeah, theoretically you could have done cosine of 30, but I just did it this way, so it'd be this piece right here that I'm drawing with the arrow, sine of 60, and it's negative. Why? Because it's pulling it down. Plus, also negative. Why? Because it's pulling it down. FB on C, sine of 60. Now, we already know that A and C and B and C are the same thing, which is equivalent to this right here. You put B there if you want, whatever makes you happy. It doesn't matter. The numbers are still going to be the same. And we have this negative. Again, negative is important. But Mr. Cooper, this is absolute value. Yes, that's for the charge. But these are both pulling it down. So the force is going down, the vector part of it. So negative 2. Why? Because I have two force A and C and B and C, and those are the same thing. Sine of 60 is going to equal, now, the negative 2 stays. And then we have our equation for force, which is this. And yes, this A could be a B if you want it to be. If it makes you happy, put BC like it's before, I don't know, whatever, and then sine 60. So again, basically what we're doing is we're just substituting for A and C, Coulombs law. And at force net on C, so the net force on C, we know is only in the y direction, right? So in the y direction equals negative 2, and that, what is this number? I don't know. Well, if you go back in your notes, you will notice that is Coulomb's constant. Just so you know. Time, so that's that Kc, 2 times negative 9 coulombs. That again, that's our A. There's our C charge. If you don't remember why, you can go back a slide, hit pause, rewind. And again, if you're following me with this because you were so lost, that's fine. It's not the end of the world. I wish you to try it on your own. But if you're so lost here, don't just wait for me to hit the answer. Hit the number in the calculator. Make sure you get the same answer as I do before I show it to you. It will help you, I promise, as silly as that sounds. Okay, so sine 60. Yeah, don't want to miss that. So equals, hopefully you've done it in the calculator. You got your number. Boom. If you didn't get that, you did something wrong. Double check it. Do it by pieces. Remember, in your calculator, don't try to do it all at once. That's redonkulous. But this would look like 9e9. Okay, that's what this would look like. Don't put 9 times 10 to the caret 9. Half the time that will mess you up. Just use that E button, which, so on your screen it will be E, but on your buttons on your calculator it will be double E. Don't ask me why they're different. I don't know. Moving on. Practice makes perfect rhyme. This is a good one. This is balloons. All right, so you rub 2-gram balloons with a wool sweater. The balloons hang at 0.5 meter long, very light string. When you attach the string together at the loop top, the balloons hung away from each other, each string making an angle of 37 degrees with the vertical. Represent the situation with a force diagram for each balloon and determine the magnitude of the force on the diagram. B. What can you say about the magnitude of forces that the balloons exert on each other? Explain. C. Will the ratio of forces that the balloon exert on each other change if the charge on one balloon is 2 times larger than another? How do you know? So what is A asking us for again? Free body diagram and the magnitude of the force. Okay, let's draw our diagram. Solution A. So we have our ball. Balloons, right? Up like that, yes? We have a balloon here, okay? Vertical. Boom, boom. All good with me? Nothing wrong? There's our angle. Why did I use that symbol? I don't remember. I just did. So this is the force of the string on balloon 1. This is the force of the string on balloon 2. This is our gravity. This is our gravity. Hopefully nothing crazy here. This is the force of B2 on B1. And this is the force of B1 on B2. Now, this is where it gets confusing. Now, understand here, this is where it'll get a little bit funky because it's not this way with the Newtonics. This is no longer your resultant force because this makes up this, right? So it's no longer a resultant force. So it's kind of like you would finger this down here like this, right? And then draw like this. So this is kind of your adjacent force. Just be careful of your angles. Draw your triangles. Remember, I over-exaggerate them when I draw them myself to make it clear what angle is what. Now, free body diagram magnitudes. Apply Newton's second law to charges. For string on B1, cosine theta. Why am I using cosine? Well, because I want the adjacent side, obviously, right? Equals mg. If I pull this down, right, and then I draw my thing right here, this mg is my adjacent side with that angle. Because my angle, hopefully you can see that. So force string on B equals sine theta equals force B2 on B1. So if one is cosine, the other one is sine. Hopefully you kind of understand that, right? If this is cosine, then this one is sine. So string on B, cosine theta equals mg. This one equals the force B2 on B1. Okay? Now, lots of letters. Just slow down and take a look at it. Now, that has to equal Kc q squared. Wait. Why is it q squared? Okay, go back to the problem. We'll go back. It's okay. It's okay. It's okay if you're confused. Here we go. The balloons, 0.5 meter string. When you're stringing together at the top, the balloons hang away from each other. Represent the situation of the balloon and magnitude. So, why do we think they're the same? Oh, because they have the same charge. You rub 2 grand balloons with a wool sweater. So it's assuming you're rubbing them with the same amount of charge. Okay? Boom. That's why. So that might have been a little funky there. Okay, there we go. Moving on, blah, 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 blah. Okay, boom. So it'd be Q times Q squared. Okay? Boom, boom. Because each of these are rubbed with the same balloon, right? So, okay, there we go. R squared being our R. So B2 on B1 is mg tan theta. Remember, this is the adjacent side like we just talked about. This is the opposite side. So mg tan theta would give us our opposite side. Taking oats away, or I don't know how you remember sine and cosine. Could be some old hippie, some old horse, or Princess Sokotoa of the Triangle Tribe. I don't know. Whatever makes you happy. So now I start plugging in numbers. But again, so we want B2 on B1 equals mg tan theta. Okay? So that's this piece. I can figure out mg. I know what the mass is. Okay? I know that this is going to be, this is the adjacent side, so this is the opposite side. And you could also plug these in. You get sine over cosine, right? And then it turns into tangent. So, okay, there we go. So mg, okay, moving on. Okay. Tan 37, because that's the angle, equals 0.015 newtons. Boom. That's B2 on B1. Well, wait, Ms. Cooper, what's B1 on B2? It's the same number. Okay. Now, force string on B1. Remember, that's this piece. Okay. Now we want the force string on B1. mg cosine theta. So I divide the cosine over. All this is Newton's second law. Boom, boom, boom. Right? Equals this. Now remember, now you might be wondering, wait, Ms. Cooper, where did this come from? Well, where do you think it came from? The mass of the balloon. But wait, we didn't need this? No, we didn't, did we? Gravity, right, 9.8. Mass of the balloon. We didn't actually need it. Could we have used it? Sure, you could go in and use this. You could figure out what the charge is if you want. No problem. But that is our force string on balloon 1. Well, what is the force string on balloon 2? It's the same thing. Okay? Solutions B and C. Newton's third law makes the forces of equal magnitude and point in opposite directions. C. Newton's third law tells us that the magnitude of the force that the balloon exert on each other are the same. Force B2 on B1 equals force B1 on B2. Therefore, the ratio B2 on B1, B1 on B2 will always be 1, regardless of the charge. Now, if you're a little confused on what I mean by that, what it meant here, if you got to go back, I apologize, I didn't put the extra. So C, well, the ratio of the forces that the balloon exert on each other change if the charge on one balloon is 2 times larger than on the other. Remember, ratio just means divide. But no matter what, no matter how many charges are on one, yes, the forces will be different. But just because A has 5 coulombs of charge and B has 4 coulombs of charge, A on B and B on A still are Q times Q. Right? So it doesn't matter. It doesn't matter if you put the A before the B or the B before the A. It's the same ratio. They're going to be the same thing. It's always going to be the ratio of 1. Hope that helps out. You may need to watch this one again. That last problem can get a little tricky. Slow it down. Try it on your own. Maybe try it without sound and see if you can make better sense of it. Maybe my words confused you. Who knows? Have a great day.